All right, 2.3 we started last time. We were talking about inverse trig functions, and we'd established a few things. Let me remind you where we were. We talked about the fact that in order to have an inverse function, we need a function that's one-to-one. A one-to-one function means that for every y value, there corresponds to only one x value. And one way to look at that or think about that is by looking at the horizontal line test. And we established the fact that every single trig function that we have fails this test. So in order to be able to use something called an inverse trig function, we have to limit the portion of the graph that we look at. So for sine and for tangent, we limited our perspective to quadrants 4 and quadrants 1, or negative pi over 2 to pi over 2. That's where we limited our picture from. And if we limited it in that way, so this is the one on sine, you can see that that little yellow piece in between there is in fact going to be one-to-one. And for tangent, same thing, between negative pi halves and pi halves, we have one smooth piece, and that piece is one-to-one. And then for cosine, we have a slightly different perspective, right? A slightly different domain. And on this one, we're limiting our view from 0 to pi. It's not actually labeled on here, but we'll label it real quick. This one was at pi. So if we looked from 0 to pi, or in quadrants 1 and 2, we actually have a one-to-one function. So we had done one example here last time of how this kind of works. And the idea when we're working with inverse functions is that we're trying to figure out what angle gives me this trig value. So if it tells me that I'm looking for the inverse cosine of 1/2, I ask myself what angle gives me a cosine value of 1/2. And I think back to the unit circle, which is why we spent so much time really focusing on that, is so that we would be able to move back and forth from those measurements. So on the unit circle, cosine values are positive in quadrant 1, and they have a 1/2 value when we're at pi thirds, or pi over 3. All right, the next one then. Yeah, I think we wrote it down wrong because I'm looking at my notes, and I think we did write it down wrong. Yeah, we definitely did. This should say pi over 6. Please fix that. I'll draw attention to that as well. It should be pi over 6 for cosine values. We should have been over here. I think we were moving really quickly at that point. I'm so sorry for having that mistake in there. It should have been down here. So it should have been at pi over 6. Please fix that. All right, we had one more that we looked at, and this one I believe we have correct. We did the inverse sign, and it was negative. It was of negative pi square root 2 over 2. So we were in quadrant 4. And in quadrant 4, we would have been at 7 pi over 4 if we were going around in the positive direction. But we're supposed to be using an angle measure that's between negative pi halves and pi halves. So if we go in the negative direction, which is clockwise, we actually have this happening at negative pi over 4. Okay? For sine, yes, we were looking for y, and then for cosine, we're looking for x. Correct. Okay, so cosine is x values, sine is y values. Any of the others are a little bit trickier to think about because we have to flip things upside down. There might be some rationalizing going on, or we're dividing y's and x's, but sines and cosines are the most direct ones for us to look at. All right, so let's take a look at some definitions. There's 3 of them here at the bottom of the second page. Inverse cotangent, secant, and cosecant. So if we're looking for inverse cotangent, it looks very similar to tangent in the fact that the domain is negative infinity to infinity. And then the range is actually like it was for cosine. It's 0 to pi. And those are the range and the domain values of cotangent itself. So if we're thinking about the graph of cotangent, let me just sketch a little picture in here. You can put yours over to the side if you would like them there. The graph looked something like this when we drew it. I had a dotted line here and here. My cotangent value, I should have extended that down. But my cotangent graph looks something like this. And so it went from 0 to pi on the domain for cotangent itself. And then the range was from negative infinity to infinity. So when we flip them, the domain is now negative infinity to infinity for inverse cotangent, and the range is from 0 to pi. Okay, so remember we're flipping domain and range when we do inverse functions. Secant and cosecant are these branches that open up and down And so you guys did that section completely without me, like with the videos. It was section 2.2. And so when we looked at cosine, the cosine graph looks something like this for cosine that we were doing it for. Yes, sir.
On that last problem, the one we did with 5 or 6.
Yep.
What's the coordinate pair for that thing? Wasn't it? There's the square root of 0, 2.
Yes. So did we have it right? Okay, my notes are just wrong then. Yeah, you're right. Thank you, Jacoby. So I did get it right. Maybe I just didn't fix it in my notes. I may have even been aware of it when we did it. It's been a weekend. So you're right. It was correct in the notes to begin with from before. So it should be right here. And then, oh, sorry, I didn't mean to put that there. This one right here would be, I'll just in yellow, it'd be 1/2 and then square root 3 over 2. And the cosine value is the x value. Yep, you're right. And sine is the y value. So cosine is my x value. So let's fix this. Go back to pi over 3. Okay, so we were right last time, and then I was wrong today, and now it's right again. So it's all good, right? Everybody has this pi over 3 in your notes, and we're good to go on that one example. Wonderful. Okay, this piece was the piece that we had for cosine, for where it was 1 to 1, right? It was just that portion of it. We isolated it from 0 to pi. And the the secant graph actually had an asymptote right here for this piece. And it had these branches. It looks like we're sort of seeing only halves of branches. But I actually only need the halves. I actually need the halves of the branches in order for this to be 1 to 1. If, in fact, I use this other side of the branch, it would no longer be 1 to 1, right? I would be running into that horizontal line test problem. So these are the portions, these two small pieces, these orange pieces opening up and down, that are actually the 1 to 1 pieces. So my domain, as you're taking a look at this, is the values from 0 to pi halves. So this is 0. At the x-axis, y-axis mark right here, and this is pi halves, and then from pi halves to pi. So that's my domain, and if I reverse it for my inverse function, that's my range. And then my range for secant itself goes from negative infinity up to the place where I'm seeing the white part of the graph, the part where it's actually cosine. And there's no orange pieces in this middle part of the graph. Right, this middle portion of the graph right here has no value that's for secant, okay? So we have this gap happening here. So you see this gap happening, right, in between the -1 and the 1. So my range goes from negative infinity to -1, and then it picks back up at 1, and it continues on from 1 to infinity. And so as we're taking a look at that, that was my range for secant, so that's my domain for the inverse secant. And cosecant is very similar. It just goes with sine instead of going with cosine. So when I'm looking at let me just draw this into, you know what, let's do that one. When I'm doing the graph for sine, the sine graph was from negative pi over 2 to pi over 2, right? And sine looked like this, roughly speaking, through here. It's not very good. That's a little bit better. And then the cosecant graph has an asymptote right there, wherever it had a 0 before, and it has these branches that look very much like the ones I just did, extending upward on the right and downward on the left. And so once again, the range would be of this graph itself, the range would be negative infinity to -1, and then you jump up to 1 and it goes from 1 to infinity. That becomes the domain on the inverse function. And then the domain for this graph would be from negative pi halves, right here, over to the asymptote at 0, and has the break, and then it would be from 0 to pi halves. And so that was the range, the domain, which is becoming the range then for the inverse function. They just flip spots. Now, all that's kind of, I don't know, it's all well and good. But the question should then be, well, how do I make use of that? We had a couple examples with sine and cosine, and even admittedly, we said they're pretty friendly when it's sine and cosine because we can identify them simply by the x or the y value on the unit circle. But for any of the others, and there's 4 of them, right? It's not quite that straightforward. So let's take a look at a couple of examples of how we deal with it when it isn't sine and cosine. So this one's cotangent, right? We start out much the same way that we did with sine and cosine last time. We write down that this is equal to an angle. I usually call it theta. And then we rewrite this in terms of cotangent. So instead of inverse cotangent, I'm writing it with cotangent. So the way that works, and you can kind of think of it like this, is that I'm putting a cotangent, not theta, just cotangent on both sides. Kind of like when we multiply by 2 on both sides or something like that, or add 7. So the cotangent and the inverse cotangent are inverse functions, so they cancel one another out operationally. And I'm left with the 1 on the left. And on the right, I'm left with the cotangent of theta. And if you prefer, you can rewrite it with all that sort of flipped around visually. It's a little bit more how we are typically seeing it. All right, so cotangent of theta equal to 1. First, we should probably figure out what quadrant we are in. So we're always going to be in 1 or 2 or 4. And this is a cotangent value. So cotangent should be in quadrants 1 or 2. That's what we established when we were looking at this slide right here. Cotangent is 0 to pi. Meant to do that. 0 to pi, right? So it's in quadrants 1 and 2. So in quadrant 1 or quadrant 2, where is the cotangent value going to be positive? Yeah, in quadrant 1. So I should be in quadrant 1. Okay, everybody good with that? Okay, we got to make sure we're in the right quadrant. And then the cotangent values. How are cotangent values defined in terms of the ordered pairs x and y? What is cotangent? Yeah, it's x over y. Very good. So cotangent is x over y. So if I want my x over y to be equal to 1, where does that happen? Or what would make that happen? What would have to happen with x and y so that when I divide them, I get 1? They got to be the same. Does that make sense? So this tells me that the x and y are the same. It's not a very good word, are. They're the same. So where in quadrant 1 do I have an x value and a y value that are the same? Yeah, it's at pi over 4. Right here, right? They're not 1 and 1, but they're the same, right? They're square root 2 over 2 and square root 2 over 2. And anytime you divide something by itself, you get 1. So at pi over 4, right here, we have the value we're looking for. So you might look at that and think, all right, Dr. Hans, that's sort of cheating. I mean, 1 was a pretty nice value. We could look at that and figure out 1 pretty okay. I mean, like divide something by itself, we get 1. What if it's not quite so nice, right? So let's do one of those two, where it's a little bit less clear what's going on. That one's a little uglier, right? That's uglier. I've got 2 square root of 3 over 3, and there is nothing on the unit circle that says 2 square root of 3 over 3. I'm going to have to work for this one a little bit more, agreed? I am. So let's first rewrite it, and second, figure out which quadrant we're in. So if we rewrite it, this is equal to theta, and we're going to take the secant of both sides. So they're going to cancel with the inverse secant on the left. I have negative 2 square root 3 over 3, and I have the secant of theta on the right. And if you prefer, go ahead and rewrite it. You don't have to do that, but if it helps you to see it, then do. Okay. All right, let's figure out what quadrant we're in. Okay, so secant. Which quadrants do we get to use for secant? 1 and 2 or 1 and 4? Right, over here, it kind of didn't matter. Like 1 and 2 or 1 and 4, I'm going to be in quadrant 1 either way, right? Because it's positive. But on this one, it matters. It's negative. So I really need to know, am I in quadrant 2 or am I in quadrant 4? Because those are the two different options for negative values. I'm in quadrant 2. Jacoby's right. I'm in quadrant 2 for secant. So cosine and secant and cotangent are quadrant 2. So if you want to make yourself just a little reminder chart, those are the three that are in quadrants 1 and 2. Cosecant, I didn't say that right. Cosine is what I meant to say. Cosine, secant, and cotangent are quadrants 1 and 2. This one is secant, so I'm in quadrant 2. Okay, so I'm in quadrant 2.
What were the three cosines, secant, what?
Yeah, so quadrants, I'll write it down. 1 and 2 are cosine and its reciprocal, secant, and cotangent. And then quadrants 1 and 4 are sine, its reciprocal, which is cosecant, and tangent. So tangent and cotangent kind of get split apart in this. But if you remember the graphs, it kind of makes sense. They're shifted one direction or the other from each other. So that's why that's happening. But yeah. So I'm in quadrant 2. All right, so, it really isn't very friendly for us to have negative 2 square root of 3 over 3. I mean, it really just isn't. It would be easier to work with sines and cosines than to work with secant. Agreed? I mean, sines and cosines are the actual values for x's and y's on the unit circle. They're friendlier. Can I change, I shouldn't say can, how? How can I change secant into a friendlier function to work with? What is secant most closely related to? Cosine. Secant is related to cosine. How are secant and cosine related? Okay, the opposite, reciprocal. And I think over here, David's going like this, right? They're flipping, yeah? Okay, so they're flipped from each other. They're the reciprocals. They're upside down from one another. So if I have secant and it's negative 2 square root of 3 over 3, I could instead look at cosine and flip this puppy upside down. Now you might think that's not any better, but it will be very quickly, just watch. We don't like things that have square roots and denominators. That's generally a big no-no. So let's fix that. How would I get that square root out of the denominator? Y'all know, so somebody tell me. Thank you. What would I multiply by back?
Would it be 2 to the square root?
We actually just need the square root of 3 part, just the radical part. If you have the other part, you'll just have more simplification. I mean, it wouldn't hurt anything. It just will end up giving you more simplification later. Okay, so let's take a minute to clean this up. So now I have 3 square root 3 over negative 2 times 3. I know I could multiply the 2 times 3, but I really don't care to. Do you see why? Yeah, the 3 in the top and the 3 in the bottom are going to cancel. And then do you see a friendlier value showing up? Square root of 3 over 2. That's a familiar value. We've seen that one before, right? That is on my unit circle. Now, it probably begs the question, what happens if I get a value that's not on the unit circle? We'll talk about those in a minute. That can happen. But right now we're focusing on the ones that are on the unit circle, okay? So, square root 3 over 2. Where are we in quadrant 2? We're in quadrant 2. We know that part. But where in quadrant 2 are we if we have a cosine value that's square root 3 over 2? Yeah, it's all the way over here. We'll actually get this one written in correctly. Right there. And that angle measure is, in fact, 5 pi over 6. Now, do you need to show all of this work? You do not. I understand that you can probably skip a few of those steps in there. But whatever it is that you need to see to be able to move forward, show something of that. Because I'm going to tell you what, you can't go from here to here and show nothing and actually have done it yourself. I mean, you can't. You did it with some sort of AI device, some sort of a photo math, something. You did it some other way. You got to show some steps in between there, or there's no way to get there. I can't get there. And I've been working with trig, a lot more than you have. So you're going to have to show something in between there to say that I went from here to here. Make sense? Okay. So let's take a look then at something called composite functions. You've seen composite functions before. You've seen them in algebra. So let me remind you what they are. So composite functions, what they are sort of definitionally is functions inside of other functions. Now, some of these things are pretty obvious. And in fact, you might be looking at it and thinking, well, didn't we just do this? And the answer is yes, we did. So these are composite functions that work out very nicely. So if you take a look at the first pair, it tells you that if you have the inverse sine of sine, right? So, sorry about that. If you have this inverse and this sine, they cancel out and they give you back the angle in the middle. Okay. That's what we've been using on the previous 4 examples. And it works if you do the sine on the outside and the inverse sine on the inside. That's actually how we've been doing it. And it works for cosine and the inverse cosine, tangent and the inverse tangent. And while I don't have slides that show you for secant and cosecant and tangent or cotangent and tangent, and they all work. Okay, they all work, but they all have conditions on the end. Do you see those conditions? Those conditions say, yeah, they work as long as you're in the right quadrant. Right? So if I'm in quadrants for sine 1 and 4, this works. For cosine, if I'm in quadrants 1 and 2, this works. If I'm in quadrants 1 and 4 for tangent, this works. I can just do the inverse thing and it works out for me. It doesn't work out quite so nicely when you're not in those quadrants. Like you can't just say, okay, well, let's just do sine and an inverse sine and then it's going to just give me the value inside. It only gives you the value that's inside if you're in the right quadrant. Okay? So let me show you a couple of examples of how this kind of plays out. So this says we want the inverse cosine of the cosine of 4 pi over 5. Now what we really would like to do is we'd really like to say, hey, let's just cancel these and let it be 4 pi over 5. But we have to make sure that we're really in the right quadrant for this to work. So let's figure it out. We're working in cosine. So what quadrant do we need to be in if we're working in cosine? We're looking in quadrants 1 and 2. And quadrant 1 and 2 means that I'm going between 0, my angle measure, and pi. So this measure right here, 4 pi over 5, does it reside between 0 and pi? Well, it's bigger than 0. Well, that's good. Is it less than pi? It is. It's 4/5. That's about 80% of pi, right? Not about. It is 80% of pi. It's smaller than a whole pi, right? It's 4/5 of a pi. So this actually does cancel, right? These actually do exactly what we would sort of expect them to do. This is going to equal 4 pi over 5. And the reason is because 0 is less than 4 pi over 5 is less than pi. That's why. It satisfies the criteria. So that's great when it works, but we need to know what we do if it doesn't work. Let's take a look at this one, 2.57. It's not a very friendly looking number because it doesn't have a pi in it, but let's start with what we need to know. We need our sine values to be in which quadrant? It's in quadrants 1 and 4. And 1 and 4 means I need to be between negative pi over 4, not 4, 2. Negative pi over 2 and pi over 2, right? Now, if you want to turn those into decimals, that will be helpful as well. If you find just an approximation kind of a decimal for this, this is approximately negative 1.57 and approximately 1.57. So if I think about those values, negative 1.57 and 1.57, what can you tell me about 2.57? It's not between them, right? It just isn't. 2.57 is not in between negative 1.57 and 1.57. It's not there. So I can't just say that this is going to equal 2.57. In fact, it's not. It's not going to equal 2.57. But what I do need to figure out is where am I if I'm at 2.57. So let's go there next. Where in the unit circle, where in my quadrants, am I if I am at 2.57? Where is that? What's that?
1 or 4.
Well, I need to be in one of the 4 quadrants, but I need to figure out where 2.57 is. It's not in 1 and 4, at least not the way it's currently written. So like this is 0, 0. This is pi over 2, and we said pi over 2 is approximately 1.57. Over here is pi. Pi is approximately what? I'll go with 2 decimals. Thank you, David. 3.14. Just for good measure, let's do 3 pi over 2. I don't know this one, so somebody's going to have to find it for me. What is 3 pi over 2 approximately? Somebody grab a calculator. I just want a decimal expansion. A couple decimal places is enough. 4.71? Okay, thank you. And if I continued, this would then be 2 pi, and 2 pi is approximately 6.28. Okay, is that okay? We're just getting some decimals. And the reason we're getting decimals is because that's how they gave us this value. It says 2.57. And I'd like to have them all in the same kind of expression so that I can make a decision. Where's 2.57 going to be? It's going to be in quadrant 2. So the quadrantal angle at the top is 1.57. The quadrantal angle over here is 3.14. 2.57 is between them. Does that make sense to everyone? That's how I'm making that decision. So it's over here somewhere. It's not a nice value that we're familiar with, right? So this is 2.57. Whoops. Okay, pretty good so far. Now, there is some value right here that is the y value. There's an ordered pair. It's not a nice, pretty ordered pair that we necessarily know, but it is an ordered pair. It resides on the unit circle. It's just not one of the ones that we've memorized. So what we'd like to do is we'd like to be able to do the sine and the inverse sine and so forth. And what we actually do is we want to reflect this into the right location. Okay? Sine values. Are sine values positive or negative over there in quadrant 2? They're positive, right? Sine values are the y values, right? We're above the x-axis. We're at a positive y value. So the sine values are over here. They're positive y values. So this is positive sine values. What other quadrant has positive sine values in it? There's 2 of them. Quadrant 1. There's also positive sine values over here. Okay, pretty good so far. Okay, I'm going to show you how you can use your calculator to sort of confirm that this is making sense in a second here. But what we're really going to do then, hang on, I need to move this because I'm out of space. Let me move it on the inside, that 2.57. Do I want to put it there? Let me just move it over here for a second. What I want to do is I want to sort of reflect what's happening in quadrant 2 back over into quadrant 1. It's a reflection. Whatever this is, right, so I'm actually asked here for what the angle measure is. This is supposed to be giving me an angle measure in quadrant 1 and 4. That's what inverse sine does. It gives me angle measures in quadrants 1 and 4. So whatever answer I give needs to be an answer that resides in quadrant 1 and quadrant 4. That's why I can't give the answer of 2.57. It doesn't reside in quadrant 1 and 4. It resides in quadrant 2. So I want to find the corresponding angle measure that's over there in quadrant 1 that would be the same sine and inverse sine, pair. And so what we're going to do is we're going to reflect this, if you will, back over here. Let's do this. So I want to reflect this to the corresponding location. Okay. Well, that's not too bad, I guess. Over here. Right, it's going to be the same height. How do I figure out what this angle measure is? Because this is the angle I'm looking for. Right, so this one right here is what I need. This angle is my answer. How do I find that angle measure? What I know is now I'll draw it in. I know that to go all the way over here is 2.57. Can't just divide it by 2, because if you think about what happens, like if you were at like 5 pi over 6, If I divided 5 pi over 6, it wouldn't reflect back over here to pi over 6, which it should, because 5 pi over 6 is the same coordinate, but with different signs as pi over 6. You can't just divide by 2. It kind of looks like it on my picture, so I apologize if my picture is a little misleading.
Can you subtract 2.57 from pi to find that other?
Yes. Yeah. So what we want is we want to find this angle measure right here, because whatever this is the same as this. Does that make sense? And if I were to go all the way over here, I would be going pi. Right? That whole measure is pi. And if I subtract off the 2.57, that will take me back up to here, which is the other portion that's sort of missing in this picture. Now, what is, I don't want you to take 3.14 because it is an approximation, though David gave us a much better one. If you take the 2.57 away from pi, what does it give you?
0.57.
Approximately?
It only gave me 2 decimal points, so yes.
Okay. I don't have it written down, so I'm going to trust that you've got that one subtracted correctly. Does that look okay when you did pi minus it? That sounds right. I think it sounds right.
Let me use the pi button.
Okay, try one more time just to be sure. I bet it sounds right.
Yeah, 0.57.
Okay, cool. All right, so our answer, our exact answer, so sometimes, my math lab says what's your exact answer? Your exact answer is that it should be pi minus 2.57. If it wants you to do an approximation, right, a decimal approximation, this happens to be 0.57. That doesn't always happen. They give you the same decimals at the end. That's why I was wanting to confirm over here with Emily. So we've got 0.57. So our exact answer is 0.57. And do you know what we were actually doing to find that? Do you know what you did? Do you know what that's called? We did it back in chapter 1. It's called reference angles. Yeah. It's a reference angle situation. We needed to find what that angle measure was that was that missing piece over there and do the reflection. All right. Let's try a couple more.
Could we write what the x's are and the y values?
Say that again.
Can we write what the x values and the y values are of each bit, like cosine?
Oh, you know what? Actually, I think that what I was going to show you, which I didn't show you yet, we'll answer that question in just a second. One more question first, JC.
I'm just confused why you subtracted pi minus 2.
Okay, so this right here is asking us to find an angle measure. So I need to find the angle measure that gives me a sine value of 2.57. Well, there's more than one angle measure that does it, right? Because the sine graph goes up and down and up and down. So there's lots of places. But this question, when it says what's the angle measure, has to be an angle measure in the correct quadrant. So there's lots of angle measures that will give me the answer of 2.57. There's lots of them. I need to find the one that's in quadrant 1. So I'm trying to find the same angle measure in quadrant 1 that gives me the same thing that's in quadrant 2. And so the value is going to be this same piece. My picture's so messy at this point. Let me draw another kind of image of it with the simplified pieces that I'm looking at. I want to find the angle measure over here that matches the same angle measure over here. And if I'm given this point all the way to here, the way that I can find that value is with reference angles. Reference angles say if I were to go all the way over to pi, and then I would go back up a little bit, I would be at the same location as I'm at 2.57. So I have pi, and I subtract 2.57. The picture is what tells me how to find that reference angle. We'll do a couple more, and it might start to be a little bit clearer. I do want to show you something in your calculator, though. Will it always be pi minus 2.57? And the answer is no.
I mean pi minus whatever.
Nope, it will not. It depends on where the angle is measuring. So I've got a couple more examples that I think will clear up how we do that. But we talked about reference angles before with that same perspective, that there's lots of formulas we could use. And so a formula approach is not a very good one because it depends on which quadrant you're in to how you find a reference angle. But the picture tells you what to do, right? Grab your calculator, though, for a moment. Make sure you're in radians, because we're working in radians here. And I want to show you that you can confirm this, at least with some level of accuracy with your calculator. Okay, so I'd like for you to do the part that's in parentheses that says sine of 2.57. Again, make sure you're in radians. I'll check mine, too. I am. So if I take sine, the part in parentheses, and do sine of 2.57, my calculator says 0.54097222204. Does yours say something like that? Fabulous. Okay, now I'd like for you to do do the inverse sine. So inverse sine usually resides underneath the sine button, but you have to press another button first. So like on my calculator, I use the second button and I hit the inverse sine, or the sine button. It gets me inverse sine. And then you can either type in that whole decimal expansion, which is fine, or if you're using a TI-84, you can do second and then the little negative key at the bottom will take your previous answer and put it there. And if you do the second inverse sine there, it will tell you it's 0.57. Okay? So what your calculator really did is your calculator found the sine value, that is the y value, right? It found the y value at 2.57. And then it found the angle measure in quadrant 1 that also gives you that same y value. And it confirms that it was 0.57, just like Emily told us it was when we did the subtraction, right? Okay? Let me look. Yeah, that's what's in here.
Okay, so about the
So if you had done it, it does not. Okay, cool. All right, everybody good to try another one? You're like, I don't know if I'm good, but let's try another one anyway. Maybe it'll start to clear things up. That's my hope. We're going to hope for that. Okay, so what we would like to do is we'd like to just mark the tangent and the tan inverse tangent out and call it 4, right? That's what we would like to do. And so sometimes we can. So, I mean, like if you're a betting person and you just want to mark them out and call it good, I mean, like you might be right. But it'd probably be better to know if that's really valid or not instead of just deciding that you're going to just take a chance every time. So if you take a look at the inverse tangent, and we have the features over here. Let's actually look back at it. Inverse tangent, it tells us that when you have this order set up, which is the one that's on our problem, tangent of inverse tangent, that this works and it will equal x when we're at any x value. Right? Anything, negative infinity to infinity. That's good news because it doesn't matter what the x value is, it's going to work. So over here, when we have our tangent of the inverse tangent of 4, this one is going to equal 4. And the reason is because, sounds kind of funny to write this way, but the negative infinity and the infinity has the number 4 between them. It meets the criteria. It's just that it's a really broad criteria on that one. Now the next one's a little weird. But I got to show the weird ones too, right? Because if you show up with a weird one later, you're going to be like, she didn't talk about that at all. So let me show you this next one. It's a little weird. It doesn't look much different than the last one, right? It says sine of inverse sine of 4. Okay, so take a look over here, our chart. Whoops, did I go too far? No, one more. There we go. Sine of inverse sine of 4. So I'm right here. What does it say my x value has to be? Between negative 1 and 1. Now think about the sine graph, right? The sine graph does this oscillating feature, goes up and down, and it bounces up and down between negative 1 and 1, right? Does it ever get up to 4? No, it never gets up to 4. It has to be between negative 1 and 1, or it doesn't actually give you a value at all. So when we're given a value that's outside of the domain, which this one is, right, negative 1 to 1, it is outside of that domain. It's not going to work. What happens over here is that there's no solution. Whoops, one more. And the reason is because sine of theta cannot equal 4. I mean, it can't. The sine value is between negative 1 and 1. Let me write down a few of those. I have some of this written down, so I think I'm going to do this right. Sine inverse of 4 is not defined because 4 is not on the interval -1 to 1. It's not there. Those actually have equals, but it doesn't matter. So this is not possible. Now, in case you're thinking, but didn't we have a 2.57 and wasn't it bigger than -1 to 1? Let's look at the difference. Check out 8 compared to 6. I know I've switched to the 2.57 for the 4, but what else is different about those two problems? Yeah, it's flipped, right? Where the sign is and where the inverse sign is are flipped. And while in some cases it sort of just cancels out and we don't think about it, it doesn't really matter, and those do happen, sometimes it does matter, right? So if you take a look at this, I can take a sine value of any value because the sine graph goes on and on forever. Its domain is -infinity to infinity. The problem is inverse sine only works between -1 and 1. Sine works everywhere, but inverse sine does not. So when the inverse is on the inside, right, this one is restricted to -1 to 1. But if it had said sine of, say, 4, like let's say that this said sine of the inverse sine of 4. I didn't say that right. Like that. This one we could work with. That's supposed to say 4. We could do this. And it would work a lot like number 6. Let's actually talk about how we would look at that, though, because 4 does put us in a different location. And I told Beck that it matters which quadrant we're in. If we were at the value of 4, which quadrant would we be in? Right, we said that this is 0. This is about 1.57. This is 3.14. What was our number over on the other one? 4.71. So we would be in quadrant 3. So if we had an angle measure of 4, we'd be all the way down here in quadrant 3. The reference angle, though, would be where? It would be this piece right here. Reference angle is always the angle back to the nearest x-axis. How would I find that value? I wouldn't do pi minus 4, would I? What would I do? How would I find that angle measure? Yeah, you're right. I would do 4 minus pi. Right? So instead of pi minus 4, I'd do 4 minus pi. And I'd be in that angle. But I'd also have an angle that's, well, not an angle. I'd also have a sine value that's negative down there, right? It would be a negative sine value. Am I doing sine? Yeah. I would be negative in this quadrant. So I'd have to be over here if I was flipping it over to here. So if I were to do the inverse sine of the sine of 4, I would actually get 4 minus pi, but then it would be the negative value of that because I would need to go in the negative direction into quadrant 4 to get there. So I would end up getting the same thing, interestingly enough, just because of the chance of, as -4 plus pi, which would be pi minus 4, but not for the same reason that we were thinking. So, all right, we have a few more things to do in this section, and we're running out of time. Let me do a couple of examples real quick, and then I think we're going to have to postpone, and you won't have homework due on Wednesday. Man, y'all got lucky. Let's see what we can get done, though. We'll do one more. Okay, so this one says, use the properties of inverse functions. F of f inverse of x is x for all the x in the domain, and vice versa on the other one, as well as definitions of inverse functions to find the exact value of each expression if possible. So these look very similar to the last ones that we were doing. We just need to make sure that we're in the right location. So this one says cotangent of the inverse cotangent of negative pi. So when we're dealing with cotangent, if we went back several slides, which I'll spare us the details at the moment, this will actually be okay. The negative pi is supposed to be between, if I'm looking at the right values, between negative infinity and infinity, which it is. This works for cotangent. Tangent and cotangents are very broadly defined. And so they go from negative infinity to infinity. So because this works, right, what this means is they cancel. Okay, which is our goal. We'd like for that to be true all the time. We don't get it to be true all the time, but we get it to be true here. Because for cotangent, we can actually go with negative infinity to infinity. So this one's negative pi. The next one's a little bit harder to work with because it's secant. Secants and cosecants don't have the same things that tangents and cotangents have. So if we take a look at 7 pi over 4, let's figure out where we are. Where are we if we're at 7 pi over 4? That is an angle measure, y'all know. Where are we at 7 pi over 4? We're in quadrant 4. Very good. So we're down here in quadrant 4. All the way over here is at 7 pi over 4. So we're in the right quadrant, but we're not in the right angle measure, right? I mean, like this doesn't actually work. I shouldn't say we're in the right quadrant. We're in a quadrant, but it's not an angle measure that we would want to work with if we were even supposed to be in quadrant 4. If we were in quadrant 4, we would want to be working with the negative pi over 4 value, right? This is actually negative pi over 4. The problem is, though, that secant is not going to work in quadrant 4. Where does secant work? 1 and 2. So I'm supposed to be in quadrants 1 and 2. All right, so how do I figure out where I'm supposed to be if I'm at secant at 7 pi over 4? Well, the secant value is positive or negative in quadrant 4. Is it positive or negative? What about cosine? Is cosine positive or negative in quadrant 4? It's positive. It's okay. So I know we think of it being below. So the y value is that it's negative, but cosine values are x values, right? So if we're on the right-hand side, the cosine value is a positive value. So our cosine value is positive in quadrant 4, which means our secant value is also positive. So if we are down here and we're a positive secant value, where else do we get positive secant values? Is it 1 or 2? It's in 1. So again, we're doing this sort of thing where we're flipping it back up. We got to be in the right place. So I need to be in quadrant 1 in order to get a positive secant value. So I'm going to be up here instead. What is the angle measure that's in quadrant 1 that corresponds to that same 7 pi over 4 or negative pi over 4? It's pi over 4, right? We reflect it up. It's at pi over 4. So I'm in quadrant 1. That's not a very good picture. How about like that? That's the same x value if I've drawn it well, which I haven't, but this would actually be pi over 4. We have to be able to get into the right quadrant that has the right sign. So we start with where the quadrant gives us. That gives us 7 pi over 4. We didn't even really need the pi over 4 necessarily, but we needed to get into the right quadrant, which is quadrant 1, so that we get pi over 4. All right, we will pick back up on example number 11 next time.